topic for today is equilibrium, specifically for parallel forces and concurrent force systems. Yes, the topics that I'll discuss today will be included in your modular exam on Saturday. Right. So let's start with a bit of an introduction. The subject matter of statics, as the name implies, deals essentially with the action forces on bodies which are at rest. So such bodies are said to be in equilibrium. So by definition, equilibrium is the condition where the resultant of a system of forces is zero. So basically, the concept of equilibrium is almost the same as our previous topic for resultant. However, instead of equating it to RD, R, etc., our equations will be equal to zero. Okay? So when a body is in equilibrium, it is either at rest or is moving in a straight line with constant velocity. So these two are the situations wherein your body is in equilibrium. So at rest or constant velocity. So let's start with equilibrium of concurrent force systems. So two forces are in equilibrium if they are equal and oppositely directed. Obviously, because if you do summation of forces, since they are equal and oppositely directed, summation will be equal to zero. Three coplanar forces in equilibrium are concurrent, and then three or more concurrent forces in equilibrium form a closed polygon when connected in head-to-tail manner. So this means you can solve for equilibrium questions using geometry. So if you want to do that, all you have to do is connect all of the applied forces head to tail, and then use geometry equations to solve for what is being asked. But for our discussion, we'll always use analytical method, not geometry. But again, if you want, you can do that. So since concepts are the same, okay, we still have your summation of forces. So now for equilibrium, summation of forces are all equal to zero. So Fx equals 0 and Fy equals 0. Okay. So let's have a few examples for us to better understand the concept of equilibrium. Let's start with number 1. And as usual, I'm going to solve this on my own, and you just have to listen. No recitation for now. So number 1, the system of knotted cords shown in the figure support indicated weights. Compute the tensile force in each cord. Okay. So in actual, all of our systems are in equilibrium. Okay. Or most of our examples are actually in equilibrium. So this means, okay, if you analyze this system shouldn't move. Okay. Whenever a system's not moving or there's no given motion, automatically that system is in equilibrium. Okay. So this is how we're analyzing that. So you have a system of knotted cords. The goal is to compute the tensile force in each cord. So you have cord A, B, C, and D. So similar to your resultant, the first thing is to create your free body diagram. So let's begin with that. Okay. So starting with your free body diagram. So let's begin with this system. Okay. So you can just draw a dot, right? And then draw what you see. So let's call this your force C. We have a force A over here, right? We have this weight. Weight is always downwards. So that's 300. And then we have another chord here. Okay, and that's your C. This is B. And recall, I said in our previous lectures, whenever we have cords, ropes, strings, etc., those are always carrying tensile force, meaning it's always away from your object. This your object, this your object. So the forces or away from it. Okay? Now next is to figure out your angles whenever you have a force and an angle. So what's given here is the angle between B and C is 105. So this total thing is 105. Another thing that's given is the angle between your weight and chord C is 30. So therefore, we know this is 30. Okay? The angles that we want are the angles from the x-axis because that is what we need to use the equations discussed previously. So this is 30, right? This is 90 degrees since they form a right triangle, a right angle. So therefore, I can easily get this by subtracting 90 and 30. So 90 minus 30, this is 60, right? And then I know that the angle between B and C is 105, then this is 60. So 105 minus 60, you get 45. This is 45, right? Again, that's just 105 minus 60. So this is your first free body diagram. I'm just gonna call that free body diagram 1. Now let's continue on to this one. So let's call that 2. Okay. So same thing, you're gonna draw your body as a point, then include all your forces. We have another weight here. Again, weight is always downward, so that's 400 pounds. Next, we have a force D, and then a force C. Okay, so once again, they're all tensile forces. Right. Now, figure out the angles. So as you can see, right, these two are alternating interior angles. We already know that this is 60. Therefore, this is 60 as well. Right? Again, and alternating interior angles. So this is also 60. Now, what about this? This is what we need. So it's here, right? As you can see, the angle from the vertical axis of chord B is 75. Once again, this is 90 degrees, x and y axis. So 90 minus 75, that's how I'll get this angle. Okay, so 90 minus 75 is 15. So this is 15 degrees. Okay, and that is my free body diagrams. Next step is to create your equations. But before that, since we have more than one free body diagram, you have to choose. And typically, okay, you choose the free body diagram, FBD, free body diagram, with least unknowns. Okay, so take note of that. Whenever you're getting equations, you choose the free body diagram with the least unknowns. Right. So looking here, let's look at FBD1. That's 1, 2, 3, 3 unknowns, right? A, B, C. And then here, that's CD, 2 unknowns. So obviously, this system has the least or lesser amount of unknowns. So we're going to start with that. Okay, so let's start with FBD2. Next step is to create your equations. Now we call these equilibrium equations, okay? So that means your Fx is equal to 0, summation of forces Fy equals 0. Again, we call those equilibrium equations. So you can start with that. We can start with either Fx or Fy. It shouldn't matter. You're still gonna get the answer. So let's start with Fx. So summation of forces X is now equal to 0, okay? It's not R equals summation of Fx anymore. For equilibrium, this is our equation. So take note of that. Let's begin. C is to the left, so sign convention still applies. C is to the left, so that's negative. C, its component, so that's cosine 60. Right? Next to the right, so plus D, cosine 15. Okay, positive D cosine 15. There's no other equations, there's no other horizontal forces. This is purely vertical, so just equate that to 0. And as you can see, there's nothing to solve for here. Whenever you have that, you can just note this as equation. And then you move on to the next equation, which is summation of forces y equals 0. Okay, let's start again at C. That's upward, therefore positive C sine 60. This is also upward, so positive B sine 15. This is downward, so negative 400 equals 0. Once again, there's nothing to solve for there. So just note that as equation number 2. And as you've noticed, we have two equations, two unknowns. You can either solve for this manually or use your calculator. Okay. And if you solve for this, you'll get C equals 400 pounds. And then D equals 207.06 pounds. Again, you should already know how to solve for simultaneous equations. Yeah, right? So now I'm done with free body diagram 2. You should move on to free body diagram number 1. So I'm going to put that here. Okay? Then you're going to do the same thing you did here. So you can start with fx or fy. Okay? But if we analyze this free body diagram, if I start with fx, right? A, B, and C all have horizontal components. So I'll have three unknowns, or rather two unknowns, since C is already solved for in my equation. But if I do summation of forces y first, I'll only have B as the unknown, so I can solve for B. So in this case, it's much more convenient to start with summation of forces y. Okay? You can still start with x. It's just gonna take a bit longer. Okay? Summation of forces y. Let's start with B. That's upward, so positive B sine 45. This is downward, so negative C sine 60. And then we have 300 as a downward force, so negative 300. And then equate that to 0. Okay. C is 400, so I can just solve that here and solve for B. B is 914.16 pounds. Okay. And then we can move on to, okay, so that's one of the questions. And then we can move on to summation of forces x equals 0. Okay. So let's start with A, that's to the left, so negative A. This to the right, so positive B cosine 45. And then positive C cosine 60. There's no other horizontal component, so equate that to 0. A, unknown. B, 914. C, 400. I can solve for A. Solving for A, you'll get 846.41. Okay? And that's how you solve for concurrent force systems. Okay? So this is method 1. Any questions for method 1? Please answer in the chat. So as you've noticed, the way to solve for this is almost the same as solving for your resultants. The only difference is we're equating everything to 0. In the previous topics, when we're looking for forces, values of forces, we're given a resultant, right? And we equate our equations to that value. But now, again, it's just all equal to 0. So this is method 1. I'll show you another method to solve for this, okay? Right? So this is your method number 2. Okay? So now, you've noticed from the first method Okay, I had to do simultaneous equations to solve for the unknowns. Now there's a way to solve around that, and it's by rotating your free body diagram. Okay, so that's your method number 2. So what I mean by rotating is taking your free body diagram, and you can do it one of two ways. First way is to decide which force will be your reference axis. Okay, so instead of creating your x and y axis, you're now going to decide the x and y axis. Okay, for example, if you want that as your x axis, you can draw it this way, right? This is your x axis, and then draw a vertical line for your y axis, and you're gonna create your equations based on this. Okay, now if this is a bit too confusing, what you can do is manually rotate your free body diagram so that one of the forces will lay either a horizontal or vertical line. For example, here, rotating it manually, you'll get that. Okay, so C now lies on the x-axis. To do that, okay, C is 60 degrees from the x-axis. So for this to go here, I'm gonna rotate the entire thing 60 degrees counterclockwise, right? Once again, 60 degrees counterclockwise. Therefore, these angles will change. Okay, that's not what we need anymore. We need angles from the x-axis or the new x-axis, which is this. Okay, so now I need to solve for these two, right? Once again, I rotated everything 60 degrees counterclockwise. So that means if D is 15 degrees, adding another 60 degrees here, that means D is now 75 degrees from the horizontal. Okay. And then same thing here. This is 75. Okay. 400, again rotated 60 degrees counterclockwise. This is its new position. Therefore, this is 60 degrees. What we need again is from the x-axis. So 90 minus 60, that's 30 degrees. And that is all that we need for our equations. Okay, so that's how you rotate your axis. Now, why do we do that? Well, as you can see, okay, I do that. And then if I take summation of forces y equals 0, you'll see that C won't be a part of the equation anymore. Okay, because now C doesn't have a vertical component. It's directly horizontal. So that's the reason why we rotate our axis. Okay, so that one of the forces cancel out or will not be included in the equation. Okay, so let's continue our solution. Summation of forces y equals 0. D is still upward. So that's positive D sine 75. We have a downward force now for 400. So minus 400 sine 30 equals 0. And from this, we can already solve for D, which is 207.06 pounds. Okay. And then afterwards, we can do summation of forces x equals 0. Okay. C is to the left, so negative C. D is to the right, so positive D cosine 75. This is also to the right, so positive 400 cosine 30 equals 0. Again, D is 207. I can solve for C. Solving for C, you should get 400 pounds. Okay? And then afterwards, you can move on to the next free body diagram. And as you can see here, I didn't change the solution because it's going to be the same. Okay? I don't have to rotate the axis because A already lies on the horizontal axis. The solution is the same for method 2, right? So you can just solve it using method 1, okay, where you're solving it as is, but sometimes it's going to be necessary to rotate your axis or to choose one of the forces as your reference axis, okay, in order to solve for the other unknowns, right? So that's method number 2. Any questions for method number 2, please answer in the chat. Okay, great. Since you don't have any questions, let's move on to number 2. And then for number 2, I'm gonna take recitation now. Okay, so number 2 is a bit easier. Let's read. Okay. A cylinder weighing 400 pounds is held against a smooth incline by means of the weightless rod AB in the figure. Determine the forces P and N exerted on the cylinder by the rod and the incline. So P is exerted by this rod on your cylinder, and then N is exerted by the incline towards your cylinder. So we're looking for those two, P and N. So as usual, we're going to create our free body diagrams. So let's analyze what's happening. Our object in question is the cylinder. Again, this rod pushes against this. The incline also has a force on your cylinder. Okay? To keep all of this in equilibrium, right? This system is not moving. So once again, this is in equilibrium. So draw your free body diagram. Okay? So once again, this rod pushes against the cylinder. So this should be our force. So that's force P. Let's choose a different color para mas kita. Okay, so that's our force P. And then in the same way, as you can see, the cylinder and the incline have contact surfaces. And whenever two surfaces are in contact, we have what we call your normal force. Okay? And normal force is always perpendicular to the surface. Okay? And that's why the question called this N, because it's a normal force. If we transfer that to our free body diagram, okay? So if this is our cylinder, right, this dot, you can draw it this way, right? This being your P, and then this is your N. Or you can draw it differently. You can extend this line of action. So instead of being here, okay, I'm gonna move P over here. So this is P, and then N is over here. I'm just gonna extend that. It's gonna be over here. Okay? And this is now your N. And then these are the angles that we want to figure out. Now P is easy, right? It's already seen here. These two are the same angle. So this is 25. This is also 25. Now how about N? You can just use your theorems on angles or triangles to solve for the angle here. Okay? If you recall your parallel angle, right? This is 55. This is also 55, right? And then N is perpendicular to the surface. So this creates a right angle. So this entire thing is 90. So 90 minus 55, you'll get 35, I believe. Yeah, 35. So this is 35. Okay? And that 35 is actually here. Okay? This is your 35. And remember, opposite angles are equal. If this is 35, this is also 35. Okay? So this is 35 degrees. So now you have your free body diagram. You can start creating your equations. Okay? So you can either start with x or y. It won't make a difference. So let's start with summation of forces x equals 0. N is to the left, so negative n cosine 35. Next, p is to the right, so plus p cosine 25. There's no other force, so equate that to 0. There's nothing to solve for, so just call that equation 1. Then move on to your next equation. Summation of forces y equals 0. N is upward, so positive n sine 35. P is upward, positive p sine 25 equals 0. And once again, that's equation number 2. Two equations, two unknowns you can solve for n and p. Please solve. What's n? Oh, correct. It's 418.60. Okay. Correct, Gian and Kenneth. De La Cruz and Bustos. De La Cruz and Bustos. Okay. This. Then what's P? Please answer. Correct. It's 378. Very good. Positive. So, correct, Kurt and Rafaela. So, Pangalangan and De La Cruz. No, Kurt. Okay. 378.35. And again, unit factors. So that's your answer. Any questions for number 2? Please answer in the chat. Oh, oh yeah. Okay. Sorry, I forgot the weight of the cylinder. Kaya pala yung iba mali yung sagot. Okay. So weight is 400 pounds. Thank you for mentioning that. But the answer is the same. So some of you already included the weight. This is the weight. This is 400 pounds. Always downward. So therefore, this should be, there's an additional negative 400 equals 0. That's equation number 2. Okay, answers are the same. So some of you already included weight in your equation. Thank you for mentioning that. Right. Once again, don't forget the weight like I did. Okay, so that's number 2. Since you don't have any questions, let's move on to number 3. Okay. 3 bars hinged at A and B are and pinned at B and C are, as shown in the figure, form a 4-link mechanism. Determine the value of P that will prevent motion. Okay. So essentially, we have this frame or system. We have force 20 here, and we want to know what value of P so that this entire system will not move. Okay, prevent motion. So that just means what value of P will put this system into equilibrium. Okay, so if we try to solve for this normally, okay, if you draw free body diagrams, right, you'll see we'll encounter a problem. Okay, so first, let's include the forces, right? So there's gonna be forces within these two rods, the same way this rod created a force on the cylinder. Okay, so these rods, or rather these members, will exert a force onto this joint. Okay, so let's call this force for member BC. There's an external force here, 20 kilonewton, and then there's another force here from AB. Okay, I'm gonna assume these forces are in compression. Okay. Again, these are just assumptions. Now, if we do it this way, okay, the next goal is to know or to figure out the angles from the horizontal. Okay. So this is what we need. And we know this entire thing is 45. Another given is the 75, right? Now, as you've noticed, it will be a bit harder to know these angles, okay, because we don't know the exact orientation of the system, right? So instead of doing that, we can do the method 2 for free body diagrams, which is to either rotate your forces so that one of them will lie on an axis, or to just choose one of your forces as the axis itself, right? So let's do that. And then I'm gonna choose FBC as the axis because we have angles from that point, or from FBC, member BC. Okay, so I'm gonna choose this again as my x-axis. Okay, so this is x-axis. And then what we need is this angle from the x-axis. Well, we already know that's 45. So this is 45. Let's actually draw this a bit better. 20. Again, this is 45. And then this is 75. But again, I need the angle from the x-axis, which is this. So this is the angle that I need. So this is 75, this is 45. Okay, if you remember from your math, the angle of a horizontal line is 180, right? This 180 degrees. Therefore, this entire thing is 180. If this is 45 and the middle is 75, so 180 minus 45 minus 75, you get this angle, which is equal to 60. Okay? So 60 degrees. So now I have the free body diagram of joint B. Next, do the free body diagram for joint C. Okay? So joint C, again, we have force in this member. Okay? I assumed it was compression here. So you should carry that assumption. Make sure your assumptions are consistent. Okay? This compression, this should also be compression. Okay? And then we have an external force here. And this is what we want, the value of P. And then we have another force for member. Okay, again, I'm gonna assume this is compression. So this is FCD, this is FBC. And like what we did earlier, okay, since I assumed x-axis is this, okay, I'm gonna encounter the same problem here. And then to make things easier, I'm just gonna assume FBC as the x-axis or horizontal axis again. Okay. Okay, again, x-axis. And then this is what we need. Okay, these two. Again, let me just fix my drawings. P. This is P. Okay, this is FCD. So these two are what we want to know. And it's already given. Angle of P from member BC is 60. So this is also 60. And then this is what we want to know. So this is 60, the middle is 45. So 180 minus 60 minus 45, you'll get 75. 75 degrees. Okay. So now I have the two free body diagrams. The next question is which should I start with? And you should start with the diagram with the lesser amount of unknowns. For this, that's 1, 2, 3 unknowns. For this, that's just 2 unknowns. So I'm going to start here. Okay. And then to start, let's start with our equation, summation of forces x or y. Okay. Again, analyzing. If I do summation of forces x, we have two forces with x components that are unknown. If I do summation of forces y, okay, along this axis, FBC is along the x-axis, so I'm going to ignore that. The only unknown will be FAB. Okay, so I'm going to start with summation of forces y. Okay, so positive FAB. Again, this is our x and y axis, right? If you want, you can rotate this to see it easier, or you can just keep it this way. Okay, so from this angle, FAB is upward, so positive FAB, sine 60, and then 20 kilonewton is downward, so negative 20, sine 45 equals 0. Please solve. What's FAB? Correct, it's 16.33. So correct Colin and Zaira. Right, and Ortiz. 16.33 kilonewton. That's not what we need. Okay. What we need is P, and then I need FBC as well. So now I have FAB, you can just store that to solve for FBC. So now we do summation of forces x equals 0. FAB is to the right, so positive FAB, cosine 60. This directly on the x-axis, so that's just negative FBC. And then this to the right as well, so positive 20 cosine 45 equals 0. We solve what's FBC. Correct, it's 22.31. Correct, Rafael and Colin, so Tabog and Terry. 2, and then Tabog. 22.31. And this is what we need for the other free body diagram. So once again, store. And then we're going to use that for this part. Okay. Again, we're concerned with P. Okay. If I do summation of forces y, okay, FBC won't be unknown or won't be included, but FCD is still unknown if I do summation of forces y. So I still need to solve for FCD, right? So I can't directly do that. So we'll just go through all of the equations. So we can start with summation of forces x equals 0. FBC is to the right, directly on the x-axis, so just positive FBC. P is to the left, so negative P cosine 60. And then FCD is also to the left, so negative FCD cosine 75 equals 0. There's nothing to solve for. So once again, just call that equation 1. Do the same for summation of forces y. Okay, FBC is directly on the x-axis, so ignoring that. P is downward, so negative P sine 60. Right? And then FCD is upward, so positive FCD sine 75 equals 0. So just call that equation 2. Two equations, two unknowns. I just want to know what's P. What's P? Correct, Rafael and Kurt. 30.48 or 47. So Tabog and De La Cruz. To Kurt. Who's Kurt? Right. So I think it's 30.47, not 48, if you use the stored value. Then unit, kilonewton. So I need 30.47 kilonewtons to put the entire system into equilibrium. And if you've noticed, all of our values are positive, meaning the assumptions for directions for FAB and FBC are correct. Okay? So that is number 3. Any questions for number 3? Please answer in the chat. How about the others? Please answer any questions. Great, let's move on to the next question. The next question already has a solution. So number 4, cords are looped around a small spacer, separating 2 cylinders, each weighing 400 pounds and pass as shown in the figure. Over a frictionless pulley to weights of 200 pounds and 400 pounds. Determine the angle theta and the normal pressure N between the cylinders and the smooth horizontal surfaces. So once again, we're looking for 2 things. This theta and then the normal pressure between cylinder and surface. Once again, there's normal force here because it's 2 objects in contact. Okay, so basically, we have this system, okay, of cords along a pulley towards this cylinder. So if you remember what I said in one of the previous meetings, right? Whenever you have a cord over a frictionless pulley, the force being experienced on one side of the cord, string, or rope is the same value as the other end. Okay, so that means, right, number 4. This is 200 pounds. Therefore, it passes through a frictionless pulley. So this is also experiencing 200 pounds. So if you draw a free body diagram, and your cylinder as the object, so that's your point, okay? This line carries 200 pounds. And it's a rope, a cord, so it's always tensile. It's always away from your object. So 200 pounds away. Same thing here. This 400 pounds, even though it's at an angle, as long as it passes through a pulley, frictionless pulley to be exact, this also carries 400 pounds. So this line also carries 400 pounds. Okay? And again, it's a cord, so it's always tensile. So that's 400. And then we have a normal force here. That's always towards the object, perpendicular to the surface. So that's upward. So I drew it this way, upward. Okay? And then lastly, don't forget the weight. This has a weight which is always downward. So downward, 800. Okay. You can also draw it this way if you want. This is your N, and then this is your 800. Doesn't matter as long as the direction is the same, and the point of application is the same. Okay. Now you have your free body diagram. You can create your equations to solve for the unknown. If you do summation of forces x, so negative 200 plus 400 cosine theta equals 0, you can solve for theta. And then afterwards, you can use summation of forces y equals 0. So n plus 400 sine theta minus 800 equals 0. Theta is 60. You can solve for n, which is 453.59. Okay. So this is just an application of a system including pulleys. All right. So any questions for number 4, please answer in the chat once again. Okay, great. No questions. Let's move on to the final question for equilibrium of concurrent force systems, number 5. The cylinders in the figure have the indicated weights and dimensions. Assuming smooth contact surfaces, determine the reactions at A, B, C, and D on the cylinders. So you have two cylinders, a blue one and a purple one. And then we want to know reactions at A, B, C, and D. Okay? Because all of them are surfaces in contact, so meaning all of them have normal reactions or normal forces as their reaction. So let's solve. Okay. So let's draw, right? I'm gonna just make this more obvious. This is purple, and then we have a blue one here. Okay. So purple force. Let's start with the purple reactions, right? So this cylinder and this surface are in contact, so there's gonna be a perpendicular reaction there. Okay, let's call that RD. Okay. Next, these two are also in contact. Remember, the reaction is always towards the object. And this is your RC. Okay. And then let's do the same for this. Okay. So we have this A towards your cylinder. Let's call this RA. We have this other one, B, again towards your object. So this is RB. And then we also have this, right? This cylinder now experiences a normal force from this purple cylinder. Okay. So again towards the object. So there. And this is your RC as well. Okay. So to differentiate, okay, this purple cylinder experiences a normal force because of this, and then this cylinder experiences a normal force because of this. All right. So the question is, what are the values of those reactions? So it's the same procedure as before, where you just create your free body diagrams. Okay, so let's start with the blue one. I'm gonna draw it here on the left. So there's RA to the right. Okay, so this is my cylinder, RA to the right. And then we have this RB upwards. Yeah. So let's draw that RB. Next, and we have RC towards the point. And RC. And then, as usual, to complete the free body diagram, I need an angle from the horizontal. So I need to figure out what this is. Okay? And that is actually, if we try to draw a line over here, right? This is the theta that we're looking for. Okay? Now, what if I did this, right? So now the goal is to solve for theta, right? And this is your theta. Now, what if I do this? I extended all these lines like so. Okay. If you've noticed, we have ourselves a right triangle, right? So I'm gonna extract that. Okay. So this is the angle that we want. So I'll just solve for that. Well, first of all, these lines are actually the radius of your cylinders, right? The radius is given. The radius of the blue cylinder is 2. The radius of the purple cylinder is 1. Okay? So if we include that in our drawing, right? This is 2. This is 1. So 2 plus 1. The entire thing, then the hypotenuse of your triangle is 3. So 2, then 1. Okay? So I have a hypotenuse. I need another leg to figure out what that angle is, right? So how do we do that? Well, let's look at what else is given in our drawing. We're given this, the entire span of your system, which is 5.6. Remember, we're also given radius of each cylinder. Okay. Very good, Michelle. Yes, the adjacent is 2.6. So let's talk about how that came to be. Okay, so how? Let's talk about it. So this entire thing is 5.6, right? But remember again, we have radius. We know this length against the radius, so that's 2. Okay, so this is 2. What else? And then this is 1, right? As you can see, this is 1. As you can see, this length is actually the base of your right triangle. So the entire thing is 5.6. So 5.6 minus 2 minus 1, you get 2.6. Okay, so this is 2.6. I have hypotenuse and I have the base. I can solve for theta using cosine. So cosine theta equals adjacent over hypotenuse, 2.6. Hypotenuse is 2 plus 1, so that's 3. Please solve what's theta. Correct, Zaira and Pamela. So Tamayo and Tamayo. Okay. Yeah, it's 29.93, and please store that in your calculator. Okay. So in case you don't want to solve for theta, okay, so from this we can actually solve for the height as well to get the slope of these two forces, right? So you can do that as well. But if you don't want to, you can just solve for the theta. Okay, so now we have theta. Let's continue with drawing the free body diagram of the purple cylinder. Okay, once again, we have this. We have RC, and then we have RD. Don't forget, we also have weight. Weight is always downward. For the purple one, it's 200 kilonewton, so downward 200, and as well as here, so this 400, always downward. So I'm just gonna move this RB over here. Okay, it's allowed because it's still upward. Okay, so RB, so that I can just draw weight this way. So weight downward, that's 400. Okay, so now we have complete free body diagram. This is theta. Okay, and this theta is this, right? Alternating interior angles, whatever this is the same here. So this also theta. Okay. So now decide which free body diagram we need to work with. Is it the blue or the violet? And then if you analyze, the blue one has 1, 2, 3 unknowns. The purple one has only 2 unknowns. Okay, so we're gonna start with the least amount. I'm gonna start here. Okay. Okay. So let's start with summation of forces vertical. So summation of forces y equals 0. RC is upward. RC sine theta minus 200 equals 0. Please solve what's RC. Correct, it's 400. Correct, Gian and Kenneth. Bustos de la Cruz. Two. It's 400.85. So that's our first answer. Unit is kilonewton. Next, continue with summation of forces x equals 0. RC to the right, RC cosine. Cosine theta minus RD equals 0. Please solve what's RD. For that, it's 347.94. It's correct, Rafaela. and Pamela. So, Pangalangan and Tamara. Actually, 347.44. If you stored the values. Okay, 44. And then, now we can move on to the blue one. Okay, analyzing. If you do summation of forces vertical, we have two unknowns. So let's start with that. Summation of forces vertical, or y, equals 0. RB is upward. RC is downward, so negative RC sine theta. And then minus 400 equals 0. Please solve what's RB, since you already know RC. Correct, Marilyn? Or Len? And then who else? Correct, Matthew. 600. It's a whole number. Again, if you use the stored values of this, we'll get the whole number, which is 600. 600 unit kilonewton. And then lastly, summation of forces X equals 0, RA to the right, RC to the left, cosine theta equals 0. Please solve what's RA. We can start with either RA or RC. What's RA? I mean, you can start with FX or FY. Correct, it's 347. So correct, Gian, 2 points ka na. So the next one is Rafael. So Pasagi and Michelle. Yeah. Pasagi. $347.44. Unit is kilonewton. And that is number 5 for equilibrium of concurrent forces. Any questions, please answer in the chat. Okay, no questions, so that ends that topic.